now we proceed and we'll have a talk from India. Let me announce a talk by Arul Lakshminarayan from south of India, so from Chennai or Institute of Technology in Madras. Arul, please, can you? So first I will ask Saverio to close his screen. Yes, thank you. And now I will ask Arul to say hello and possibly try to share your screen.
Yes.
So we'll have a talk from India now. Yes. Yes, now it's larger. Thanks. Arul, please say something.
Hi, Carol.
Yes.
Yes. All right.
Great. Yes, go ahead. We can hear you.
All right. Very nice. So first of all, thank you so much, Vinayak, Carol, and Francesco, for putting this together. And it's a unique event, and I'm actually honored to be here and meeting so many giants. It's very memorable and remarkable. And I must confess that I'm a little bit nervous too, as to exactly what I'm going to say. So I'm going to talk about some work which relates to the SMR paper, but I must also say that I'm not a deep thinker in the open systems world. But I believe that there are ramifications beyond that, and I hope that I bring that out. And Carol, okay to be technical. I will be technical, but not in great detail. So, yeah. So this is the famous paper that has been discussed, and it's a very nice presentation.
Yes, note here that we have two equations, number 14, and both are very important.
So actually, I did find that the published one had various scrambled, numbers. So there was also a 14 prime and so on. So I'm not 100% sure of the typesetting at that point. But anyway, so this has already been shown by Carol, the first equation here, this equation 14. And it says that here we have a state as expressed as a density matrix, and it's the most general evolution given linearity. And this is the new density matrix at a later time t. And this is what we now call a super operator. And this properties of this are a little bit obscure, let us say, but there is a certain rearrangement of this matrix. And let's say that the density matrix is in a Hilbert space of dimension n, then this is an n squared by n squared matrix. And there is a rearrangement of it, as mentioned by Carol. And the rearrangement is very simple. So here we look at this A. These are the indices Rs and R prime S prime. It's a very curious exchange where one exchanges R prime and S. So the second index of the first couple and the first index of the second. Okay, so that's giving you this new matrix B, and it turns out that that's a Hermitian matrix. And there has been a discussion also about its positivity, which is very crucial step. So let me actually try to, in my own way, talk through this paper in an absolutely simple way. I'm sure I'll be making errors, but bear with me. So let's take a matrix. I'm going to start absolutely simply. Let's take a matrix A in some representation I alpha. That's the matrix element. So there is a vectorization procedure where we vectorize this matrix A in this following manner. It just says that you take a squared matrix, you go along the rows, put it in a column, put it in one column, and that's a vector. So you take an n by n matrix, you get an n square dimensional vector, and that's a vectorization. And this is an era very different from the one where the SMR paper was written. So if I say vectorization, we can Google and see what Wikipedia says about it. So this is called a row major vectorization, as I've written it down here. And there is a very interesting simple identity, which says that the vectorization of a product of three matrices is given by this identity. So it's a matrix multiplied by the vectorization of the matrix. Did I make a mistake? Yes, I did make a mistake, I'm sorry. Please interchange B and C mentally. So it's the central matrix, which is here, so vector B, and this is A tensor C transpose. So the one at the first and the third points. So this is a simple identity to verify. Now, let's go back to quantum mechanics and apply this linear algebra bit to it. A quantum evolution, let's now look at a unitary quantum evolution, not the most general, therefore it's closed system if you wish. And a density matrix is evolving according to this equation. And now let's vectorize the equation. So these are n by n matrices on both sides. Vectorize it, you get an n square dimensional vector, and that we will denote by this, rho prime. And we now apply this identity. And A and C are U and U adjoint. So U adjoint transposes its conjugate. So U tensor U adjoint times rho. And this is the super operator. So you see, now when we have gone from this Heisenberg or the adjoint picture, so to speak, to the super operator picture, we have doubled our space naturally. We have gone from an n to a tensor product of that. A copy of that space has been made. And the super operator is simply here, U tensor, U adjoint. Now, how does one generalize this, so to speak? But before that, let's look at this curious operation, which was introduced perhaps, I don't know whether for the first time, but it was definitely introduced in the SMR paper, and which I'm going to call realignment, as it has been called realignment. Again, I'm not sure by whom first, but definitely it's there in the literature as one of the words is realignment. So let's take this matrix L, which is now an n squared by n squared matrix. And so it has two indices here, as opposed to this one index there. So there is I alpha, J beta, and the realigned version of it is written as LR. And again, you just interchange the second and the first from this. So you get IJ and alpha beta. Okay, so it's a simple thing. And now let's look at what happens to this super operator U tensor U star under this. So you have exactly this operation, and so you can see that the realigned version of the super operator is nothing but a one-dimensional projector, which is this realigned, the vectorization of this unitary operator, which you started out, and it's the just an outer product with this matrix here. And this can be written in one step, maybe if one takes this identity for granted, that tensor product of two matrices realigned here, so this is this R operation realigned, is simply given by this one-dimensional, rank one object there. Okay, so now what's interesting is that we have now a dynamical matrix. So this was what the terminology which was introduced in SMR, which is a positive matrix, which is here, but this is a unitary evolution. So when we generalize this, and now there is a gap, which was also discussed just now, but let me skip that gap, and all the technicalities and subtlety is very important. But let me skip that for a moment and say that the most general in the CPTP, completely positive trace preserving quantum evolution in this Hilbert space is then a positive definite realigned matrix LR, and that can be diagonalized because it's a positive definite matrix, and therefore these are the eigenvectors. And then if you go back to the super operator, you now make use of this identity, and you can write this as a product of these matrices which are there. And you can think about this as a Schmidt decomposition of the super operator. And then the action, or the new density operator is nothing but this, and which is now called the Krauss operators. You can identify the Krauss operators from this, and as the Krauss representation of this, or the Krauss, Sudarshan, Mathews, Rau representation maybe. So this is the most general possible evolution of a quantum system. So this is, roughly speaking, the a framework, and this is from this very nice paper, which I would recommend anybody who's not familiar with this, by Carroll and Jamar Bengtson, on the duality between quantum maps and quantum states, 2004 paper. There are many tables, but this table is summarizing the properties of the superoperator versus the dynamical matrix. Hermiticity, no. The dynamical matrix is Hermitian, and there are constraints on the states. The eigenvectors are essentially the Krauss operators in the case of the dynamical matrix. And we will actually look at the eigenvalues of a superoperator in a minute. And the unitary evolution, as I said, is given by this. So that's the superoperator is U tensor U star, and the dynamical matrix is given by this. You can talk about entropies and so on. Let me not go into that. But let me also point out that one particular transformation, which is a completely depolarizing channel. That is, you take a density matrix, and the channel or the transformation is such that it's replaced by the most maximally mixed channel. So this is a completely depolarizing channel, but the final density matrix is maximally mixed. I is the identity. In this case, the channel itself, or the superoperator itself, is a rank 1 object of this kind, where phi plus is a maximally entangled state. And one can see that this is the case because the realignment of this maximally entangled state is the identity. So this is something which is a quite easy thing to see if you just take a 2x2 matrix, as I will show in a minute. Yeah. So let's go back to some linear algebra here and see what exactly is this operation doing. We all know what a transpose does, matrix transpose, whereas these operations are a bit more weirder. So we will have a matrix X, which is now considered to be in a product space because that's where our operators are living, like the dynamical matrix or the superoperator. And that's coming from the doubling operation, which we just did. So it's an n square by n square matrix. And you can label these by these two indices I alpha. And then this is the realignment operation, which I've reproduced from the SMR paper. But actually, I am now doing something slightly different. I'm interchanging not alpha and j, but the first index and the second index. So this is another complementary operation of realignment. I'm calling that R1. So clearly there are two possible operations where you're interchanging the second and the first, or the first and the second of these two pairs. So you have an R1 and R2. R2 is what came in the SMR paper. So for example, if you take n equals 2, it's a 4x4 matrix. So this is for qubits in the modern jargon. And here is a 4x4 matrix, nothing special about it. You've just labeled it by these pairs of indices 0, 1, 0, 0, etc. till 1, 1. Then the realignment procedure, which I've done here, is just saying that you split this into 4 2x2 matrices, and you take the first 2x2 matrix and you vectorize it. You vectorize it, as I've said. So these are just matrices filled with vectorizations of these sub-matrices. So that gives you this XR1. And XR2, which is what appears really in the SMR paper, is this vectorization along these rows. And then there are these two other operations, which I don't know whether, I would imagine that they came after me, but please, after these operations here, but please feel free to correct me, are the partial transposes. That is, we all know what a matrix transpose is, but here now you transpose within these blocks. So you are transposing within these blocks. And the other transpose is a closely related thing where you're doing a block transpose rather than transposing within these blocks. So there are actually, this is transposing with the blocks itself. You can see the red and the black that is interchanged here, the red and black. Here, the red and black are kept as it is, and you are doing a partial transpose within these blocks. Okay, so now all this looks like a bunch of, and it is a bunch of permutations, some random operations on a matrix. What's important about it, and what's nice about it? I think that why these permutations? There are so many other permutations you may make on the matrix. Well, first of all, they're all related, and they are related by this quantity called swap, which is another permutation. And the swap is just interchanging these two indices or two subsystem states, I alpha to alpha I. And just put down a bunch of things. We know that if you do a partial transpose on both the subspaces, that's equivalent to a full transpose. And similarly, these two realignments, they are also related. So we don't really have to worry about whether you're doing R1 or R2. They are related, they have the same spectrum, for example. And they are related to the transpose through the swap operation. So the swap and these four permutations, they are in a very close relation with each other. And this is, I would say, the real reason why these things are important is that they are in some sense covariant with respect to multiplication by local operations. So these are local operators. And as you can see, if you multiply a matrix by local operators on either sides or both sides, and then take any of these operations, they are still locally connected with these permutations here. So this is what makes these things, I would say, gives it the importance of these. And therefore, they are also closely then connected to properties of entanglement, state entanglement. So now I'm going to do something quite different. We took a super operator first, and that was a motivation. We did a realignment of that. Now I'm going to take states. So, and then do realignment of the states themselves. So these are actually now states which are in a bipartite system. Earlier, we were just looking at a state in one dimension or a single state. We are now going to look, it could be also a state of a single particle. This is a state which is already bipartite. So like this. So, and then there is this important notion of entanglement and separability. A separable state is something which is a convex sum of product states such as these in A and B. And it's an important question, given a state rho, to actually find out if it is separable or not. If it's not separable, we'll call it entangled. This is even now an open problem. It's not an easy problem. It's known that it's a hard problem. And these two relations, a partial transpose, as I've introduced it, as well as the realignment, have answers to this question, partial answers, but important answers. So the Perez partial transpose criterion says that if you take a partial transpose of this density matrix, and if it's negative, then it's entangled. And so also, strangely enough, the realignment criterion has, the realignment criterion states that you take one norm of this realigned matrix. If it is larger than one, then the state is entangled. So these are sufficient conditions on these states to be entangled. And this one norm is just the sum of the singular values of a matrix here. So as you can see, then these two operations kind of one had its origins in the SMR paper, have ramifications which are now going into entanglement. And these are actually just realignment and partial transpose applied to a state. I would just emphasize it again. And now let's come to a much more recent time. I'm just looking out for, yes, much more recent time, 2019. So this was a paper written in 2019, exact correlation functions for dual unitary lattice models in 1+1 dimensions by these authors. And I've just taken a screenshot from that. And it says that if there is a unitary operator U, we introduced the dual local gate U tilde by means of the following reshuffling. So this is your original unitary matrix, and these are the indices J, L, and IK on the bipartite system. So again, now we are imagining a bipartite unitary operator. And you can see what they're doing. They're interchanging the first and the last index on these two. So J and K have been interchanged. The one has been left in between. And this is just a realignment as we talked about it. So the dual operator of a unitary operator is nothing but its realigned operator. And why exactly is the word dual is there is a space-time duality, and that is this, as we have expressed it here. So the strange operation on the matrix can be considered as an interchange of space and time in the following way. Let's look at a unitary operator's matrix element, bipartite again, and think about this J beta as input indices. And then this is some machine, which is then spitting out at this I alpha as the output indices. And then you have some amplitude or whatever for this operation, which is just this matrix element here. So we would think of these as inputs, J beta, and these as outputs, I alpha. So then you would think of a vertical direction as time. Okay, so this as time. So now what happens if you look at, and J beta are two indices. So you can think of them as input from two particles. So there are two particles at two sites. And so you would think of this as a spatial direction, the horizontal one. And now let's look at a realigned operation. Here is R1 as above, where we have interchanged I and beta. So beta and I here. Now this is this blue operator, which I've now expressed in this color here. Actually, I've made a mistake here. This input should be I and J. So again, I, J, and alpha beta on top. Okay, so you can read from the top down if you wish. But this is the pictorial representation of this. And what has it done? Now this alpha beta, which was along the time direction, has now become along the horizontal or spatial direction. And Ij, which was along the temporal direction, is now become along the spatial direction. So there is a space-time rotation that has been done. And so this is the dual of this unitary U. And why is this? So this is exactly the operation, and R2 has a very similar, it's just a rotation about the other side and in other direction. So why is this important is that it has enabled one to solve many models exactly. And that's what I would like to talk about just a little bit here. So here is a much more broader, this is just one unitary operator, but now you can think of many particles, let's say 2L particles, which are arranged on this lattice. And there are now interactions between them, which are these unitary operators, U. So you have an interaction between these two, and then between these two, and so on, which are given by this unitary operator, U here. And in the next time slice, now you're going to look at this vertical as time. The next time slice, it's now interaction between the other pairs which were not interacting. So it was nearest neighbors here, and then the other nearest neighbors start to interact. So this one is now got input from these two, and then it's done. So actually, these are nearest neighbor interacting particles, a very popular model, of course, of many-body physics. But now these are unitary operators, so they are kind of Floquet systems here. And this is spatial direction. You have all these particles, 2L particles, and this is time. And so there is this gigantic unitary operator of this many-body system, which is expressed by this calligraphic U. What one wants to calculate, for example, could be something like this: trace of the power of U, trace of the propagator, or Green's function of this kind. which is sometimes a hard thing to do, often a hard thing to do. Now, if you were to now reverse or rotate yourself or rotate this diagram by 90 degrees as we did, and look at it from this direction, look at this spatial direction as if it was time, it's equivalent to 2t particles. So time and space get interchanged. Now the propagator is this realigned unitary operator, U tilde, and time now becomes space. So this is equivalent to trace of this dual to the power of L. So
5 minutes, Arul?
Yeah.
5 minutes, okay.
Yeah.
Okay, 6 for you.
Thanks, Karen. So, right. So, so let's recap. So we first did a realignment on the super operator, then we did it on a density matrix. Now we're doing it on a unitary operator, on a bipartite unitary operator. And the significance of these are, we saw one a dynamical matrix, the other was entanglement properties, and now these dual properties or the dual operators enable us to solve many-body problems. And here is something which is called a dual unitary. If after the realigned operation, your matrix remains unitary. In that case, it's of course a very special matrix, and it's called a dual unitary matrix. And dual unitary circuits made out of these are actually solvable in a sense, which I will tell you about. But more important, immediately, it's of importance to note that a matrix U, which is dual unitary, such that the realigned U is also unitary, is a very important one as far as its entanglement properties itself is concerned. It is one of a maximum operator entanglement. Okay, so if we think about entanglement not only of states but as operators as well, then unitary operators which are dual, that is its realigned operator is also unitary, is maximally entangled. It's quite easy to see from, again, a Schmidt decomposition, and then we can introduce an operator entanglement, which is maximum if this realigned matrix is identity and it follows this. So these identities here, if it is a dual unitary, you see these kind of contraction pictures are very useful in solving for many-body properties such as this. So you have a large circuit, you can find out correlations between two operators which are separated in space-time and analytically. And in fact, let me skip over some details. But what is remarkable about these kind of dual unitary circuits, as I've shown here, is that correlations vanish everywhere except on the so-called light cone. So suppose you have two observable single particle observables which are here and here, single particle operators which are here and here. They are connected by this line, and it's only on this line of that the correlations are non-vanishing. So if this operator is anywhere inside the light cone, it's zero. The correlations are strictly zero. So it's only non-vanishing here and on this corresponding thing. And this is given by the properties of a CPTP map. So we kind of come back to the notion of a map. So this is, you can think about this many-body properties as being given by the properties of a CPTP map of just constructed from a single qubit or a single particle. It need not be a qubit actually. So let's come back to some environment kind of picture. So now you can forget about the many-body system and just talk about two particles. And there is this unitary matrix U. This is a single particle density matrix rho, sigma here. And this is an overall evolution of this U. Now you trace out, usually one traces out the environment, but here you trace out the system and you get this map M plus, which determines the correlations along this. Yeah, so these maps are themselves can be written in terms of this partial transpose and realignment. So these operations keep coming up all the time. And let me just skip through these. things, but just say that the spectrum of these CPTP maps or these Liouville operators or super operators now, which are not real anymore, I mean, not necessarily real, they lie inside the unit circle, and they determine how these correlations decay on this. So this gives you information about the dynamical properties of such a many-body system. And you can classify these many-body systems then according to an ergodic hierarchy, ergodic, mixing, and so on. And at the apex of this hierarchy is something which is which we call Bernoulli, which is such that all the eigenvalues of these channels or the super operators vanish, except there'll be one which is equal to one, which is a trivial eigenvalue in some sense. So in this case, correlations decay everywhere in space-time. So it's a very strongly decorrelating system. And these are constructed out of these operators, which are called Bernoulli. And these operators, which create these kind of highly decorrelating operators, are very special. They come from operators U, which are unitary, but also their realignment is unitary, so that it's dual, as I told, but also its partial transpose is unitary. So these are very restrictive conditions on this unitary matrix, that all of these permutations, both of these permutations are also unitary. And you can construct a state out of such a unitary operator, just like this. Now it's a four-party state, and this state has a very special property. They are absolutely maximally entangled, if all of these things are true. That means you can take any cut of it, it's maximally entangled with the other. So these were described by Dardo and Carroll and co-workers in this paper. Absolutely maximally entangled states, combinatorial designs, multi-unitary matrices. So two unitary matrices are those which maximize entangling power of this. So not only are they dual and have maximum entanglement, but they are in some sense the most possible, maximum possible entangling power they have in a very strict way. Okay, so I think I will sort of rush through these things, but let me also say that there are no two unitaries for Q equals 2, that is qubits. So this is related to the fact that there are no absolutely maximally entangled states of 4 qubits. I've already said something about Bernoulli. So how do we exactly construct these? How do we know that they exist? How do we construct this? There are many, it's a bit of an art. So they're based on some block diagonal constructions. Then they come from combinatorics, things like orthogonal Latin squares, dynamical systems, Fourier transforms and their generalizations, and some nonlinear maps, as we discussed in this paper with my student Suhail and postdoc Aravinda, who's now a faculty somewhere else at IIT Tirupati, in fact. So let me actually skip this and say that two unitary gates, that is unitary operators such that both their partial transpose and realignment are unitary, exist for all n greater than 2. The n equals 6 case was not settled positively, but I'm happy to say that recently with Carroll and his students and Suhail, a student here, we have settled this positively. And it's there in this paper called 36 Entangled Officers of Euler Quantum Solution to a Classically Impossible Problem. So time will not permit me to go into details on that. Let me just say that it solves a puzzle of if there are absolutely maximally entangled states of 4 states, each of dimension 6. I'm just saying, I'm just displaying here a state that actually exists, such a 36 by 36 unitary operator. And it has all of these things which are unitary. We call it a golden state because the golden mean plays a very important role in this. So this is the last slide, Carol, and I've called it the last slide, therefore. The SMR paper continues to stimulate our understanding of quantum information theory, many-body physics, open systems, quantum chaos, and much else. And I must say, I mean, it's Professor Mathews, Professor Rau, I'm really happy to see you here, and Professor Bhamati also. This statement would make sense to all of us who knew the first author, and I knew him only very slightly. While dual operators have played a central role in this talk, ECG, as is more popularly known in India at least, was a non-dualist. He believed in a unity of a very philosophical sense. And Sudarshan was most taken up by problems of irreversibility and time, as I've heard in a few conferences. And I end with a quote of his. There are certain fundamental questions in physics for which there are no clear-cut answers. For example, what is time? I breathe. I count the number of times I do that. Can we call those intervals as time? Suppose I stop breathing. Does time cease to exist? Carol, I know I'm 2 minutes, 40 seconds over time. I should ask your forgiveness on that. Thank you, everyone. Thank you for this opportunity.
Thank you very much. Thank you, Arul.